Hi, my name is John and welcome to another edition of Statistics Quest. Today I want to talk to you about type 1 errors, and this is going to be a little controversial because it's going to buck conventional wisdom, okay? But hopefully by the end you'll see why I and other experts that you can find online contend that type 1 errors are in reality much higher than we believe they are, okay? If you have not had a statistics course where you talked about hypothesis testing, p-values, type 1 errors, you may not understand some of this. However, most of the mathematics is actually very basic. So hang in there. If you have any questions, always feel free to put them in the comments and I will be glad to get back to you as soon as I can. Let's first define what a type 1 error is. Type 1 error is rejecting HO when HO is true. Excuse this little mess here. Okay, HO is H sub 0, that's the null hypothesis. Very often it's written as there is no difference. So for example, there is no difference between a drug and a placebo when trying to improve some condition. That's the nature of H sub 0. And H sub 1, which is the alternative hypothesis, sometimes written H sub A, is that there is a difference, okay? But a type 1 error is when you reject HO, which is actually supporting H1, when HO is true. Or in the illustration I just gave, it's when you reject that there is no difference when there is a difference, okay? Now, the way we go, the conventional way of going about this, as far as p-values go, is that we have this normal distribution. Usually it's a normal distribution. And we assume that there's no difference, okay? And we take a sample, and maybe the sample is kind of an outlier. And we say, well, okay, we're going to assume there's no difference, H sub 0. That's the assumption. It's kind of like the accused is innocent. And if we find extreme enough information, we're going to find in favor of H1, which, to make an analogy to a court trial, is the accused is actually guilty, okay? So this might be such an example where we find an extreme example, okay? And it's extremely far enough away, sufficiently far enough away from this no difference that we conclude that, well, even though there might be no difference and we get an extreme or fluky value, since fluke values don't happen that often, our assumption of no difference must not have been correct. So we're going to conclude there must have been a difference. In other words, this assumption must have been faulty for the fact that we got an extreme example. And the way we end up putting a probability to a type 1 error is actually the tail area. And depending upon whether it's a one-tailed test or two-tailed test, it's some small area. It's actually the tail area that's more extreme than what you found. Okay, and again, I just glossed over this. If you might recall, that's the basic premise in a statistics course, okay? But the reason I glossed over this is I'm contending that even though on the surface this may seem correct, the best way I can phrase it is it's kind of like looking through a vacuum, in a vacuum, where the way that we conventionally look at p-values is distorted. I'm going to leave it at that. I'm not going to call it wrong. I'm going to call it distorted, okay? Now, what do I mean by that? All right. P-values, I think I said at the beginning, is they're actually likely to be much higher than stated. So let's just say we are testing at a significance level of 0.05, right? Again, for those of you familiar with hypothesis testing, a significance level, sometimes represented by the Greek letter alpha, very often is 0.05, sometimes we have 0.01, sometimes 0.10. And we're going to test that a supplement reduces cholesterol, okay? we take 1,000 tests. Now, when we say we take 1,000 tests, what do we really mean by that? There's this universe out there that none of us really know about, okay? And we take educated guesses as to what that universe holds with respect to these tests and, in this case, the likelihood of a supplement reducing cholesterol. So we take 1,000 tests or pretend that 1,000 tests could be taken, and maybe there are 1,000 different supplements, but they're all of the same nature. And we speculate, again, we don't know, that there is a real difference that this supplement makes in cholesterol 20% of the time. Well, that's 200 out of 1,000 times, right? And there's no difference 80% of the time. Okay. Well, of the 200 times that we are speculating there might be a real difference, we believe that we will find that difference 80% of the time. That's actually called the power. The power of a test is the probability of finding a difference where there is a difference. So if there is a difference 200 times and we find a difference 80% of the time, we're going to find a difference 160 times of the 200 times, which means we find no difference 40 times, okay? Of the 800 times, there is no difference, okay? With a significance level of 0.05. We are going to find a difference 40 times just by chance, 5% of 800, okay? Just by chance. This is basically kind of this extreme example situation. And we're going to find no difference 760 times. And what's happening is, and again, this is kind of the distortion I talked about, is the probability of a type 1 error is usually defined as this number over this number, which is 5%. But let's think about what's happening. The probability of a type 1 error is making a mistake with your statement where you reject HO where HO is true. Now, how often are you going to find a difference, which means reject HO in this case? You're going to find a difference, which means you reject HO this many times, 160 plus 40, that's 200 times, and you're going to be wrong 40 of those times because there was no difference 40 of those times. So what is the probability of a type 1 error in this case? It's not 5%. It is actually 20%. It's 40 out of the sum of this, which is 200. 40 divided by 200 is 20%. Okay, and this I have written at the bottom here. So going back to the first example, we are wrong 20% of the time. We reject HO 200 times. We find a difference that we are wrong, as we said, 40 times. That's 20%. Okay. I'm going to go over some examples where we're going to see how often we're wrong depending upon two key things. How often is there a real difference? And what is the power? Okay, which we defined earlier. Again, we don't know both of these things. We can take educated guesses just based on history, wisdom, experience, etc. First example we already went over. The real difference was 20%. The power was 80%. We're 20% of the time we are wrong when we make the statement that we have rejected HO. Okay? That's the probability of a type 1 error. Second example, and again, I'm just arbitrarily making these up. What if the real difference is 20% and the power is 90%? If we go through that same tree diagram, and you might want to do this on your own, and it's actually a good idea because, even for myself, as I went through these numbers, it crystallizes exactly what's happening. And it's really just a matter of numerators and denominators. And if you find the numerator and denominator, just like I did in the first example, you're going to find it's about 18%. So what happened? As we kept the real difference the same and we increased the power, we actually improved our error rate, so to speak, from 20 to 18. So increasing the power, keeping everything else the same here, will improve or we could look at it vice versa. If we had tried in power of 70% with a real difference of 20%, again, this is with 1,000 tests, we would be actually wrong more than 20% of the time, okay? So it would go in the other direction. Third example, let's compare the second and third example. Here I kept the power 90%, but this time I dropped the real difference to 10%. Again, if we go through the tree diagram, 33% of the time we are going to be wrong, meaning that type 1 error is actually not 5% or whatever our significance level is. In this case, it's 33%. Okay. This is just the third example. I wanted to put this on the board just to kind of clarify, very similar to the first example. So again, I already said 33% wrong. Why? Because again, doing the same thing, 10%, 90%, right? We get 100, 900. If we have a power of 90%, which was what the third scenario suggested, we are going to find a difference 90 times. 10 times we don't find a difference. What are we going to do? Out of 135 times, this plus this, that we found a difference, 45 times we made a mistake. 45 over 45 plus 90 is 33%. Actually, 1/3, approximately 33%. Okay. Now, I just made up one other example. What if the real difference was 50%? We would find it's only a 10% error rate. So in other words, this is going in the other direction. So the higher the real difference is, the lower the probability of a type 1 error makes. And here's what's kind of happening intuitively. The higher the real difference is, that's actually inflating the denominator, hence reducing the error rate. Again, if you play around with these numbers, you'll see that. I made up an extreme example. What if you claim that if you drive a yellow car, you can reduce cholesterol? Okay? And we do this 1,000 times. Well, again, keep in mind what these branches are. This is the real difference percent time, which we said we don't know. But in this case, we're going to say that we do know, because we're going to claim, well, yeah, driving in a yellow car is not going to reduce cholesterol. So if you do this 1,000 times, there is never a real difference. But here's the thing. So 100% of the time, it is going to be there's no difference, right? 1,000 times. But you're going to find a difference 50 times just by chance. Remember that normal distribution we showed? You're going to find a difference where you believe there is a difference statistically. What's the probability of a type 1 error? There were 50 times you found a difference, and all 50 times you erroneously found a difference. That's 100% of the time. You made a type 1 error 100% of the time. Obviously, this is an extreme example, right? It's not going to be 100%, but this should bear out how the numerators and denominators work towards driving that type 1 error. Okay, what to do? There are several mathematicians that have studied this. Actually, from what I found online, Berger, I think, does a very nice job. He uses actually Bayes' theorem, some algebra with some assumptions, and basically looking at different possible distributions and things like that. It's actually, if you're interested in it, I can always provide you a link, or even, I think there are several links that might illustrate this. But so he came up with an equation that says alpha of p, which is the p-value, is equal to 1 over this expression, okay? This is e, which is approximately 2.71, and this is the natural log of p, okay? And you can just plug in, you can use an Excel sheet really to plug in numbers. And so, just to give you some examples, if your p-value, let's just say is 0.05, okay, which is very commonly used, as we said earlier, alpha of p, which is his estimation of, it's kind of like looking at all possible scenarios of what your type 1 error rate might be. He is saying that in reality, on average, your error rate is going to be about 29%, not 5%, okay? If your p-value is 0.01, that seems to be relatively small, right? If you've done these hypothesis tests, 0.01, oh, that's pretty low. Well, Not so fast. This equation would say about 0.111. So you're intending to make a mistake only 1% of the time. You're actually making a mistake 11% of the time. So if you really want your probability of a type 1 error to be small, let's say 0.05 or less, you should make your p-value when you're doing your hypothesis test, or excuse me, your significance level, I take that back, you should make your significance level, which is your criterion, to be somewhere here, because somewhere in this range is going to translate to an error rate for a type 1 error between about 2% and 7%. So in fact, if you want it, 0.001 is about 2%. Okay, again, this bucks conventional wisdom. Some of you may disagree with it. It actually contradicts textbooks, etc. But it's basic math. It's basic math. Again, I want to illustrate, we don't know what that universe holds, but with some basic assumptions of what the universe might hold, and I did make some reasonable assumptions other than the yellow car, right? When I said 10% real difference, and when I said the power was 80%, we see that the probability of a type 1 error is actually much more than 5%. Okay? Again, if you have any questions or comments, feel free to leave them in the comment section. But thank you for tuning in to Statistics Quest. Don't forget to hit the subscribe button, and I will see you next time on this channel. Thank you.